Hey guys, welcome back to Explore Electronics. Let us continue our discussion with respect to the subject Advanced VLSI. Let us move on to the second half of the module 3, that is data types. In our previous videos, we have discussed verification guidelines. Let us move on to the coding aspects of this module, starting with data types. What are data types? The data type is a type of data we are going to represent. It allows us to allocate some particular data value to a variable what we are going to declare with that data type. So with respect to the test bench written in System Verilog is concerned, there are many data types added in System Verilog compared to Verilog. So this is the major difference between the System Verilog and Verilog also we can say. So System Verilog introduces new data types with following benefits. There are two-state data types. Two-state in the sense these data types will be allow only 0 and 1 values. It will not allow x and z values. Those are two-state data types. It will be used for the better performance and reduced memory usage, and also it will allow us to allocate only the known values. Then we have queues, dynamical arrays and also associative arrays in System Verilog. It will be used to reduce the memory usage, again built-in support for searching and sorting. And then classes and structures. As we know, System Verilog is more powerful compared to Verilog because of the OOPS concept introduced here, that is classes and structures. And this will support the abstract data structures also. Then unions and packet structures are introduced in System Verilog. These allows multiple views of the same data. And then strings, we have built-in string support here in System Verilog. And then the very important data type, that is enumerated types. Using enum types, we can make the code easier to write as well as to understand. So let us get into these concepts, that is part of module 3. The very first thing is we need to understand which are all the data types available in Verilog and in System Verilog. The first table indicates and gives us the information like Verilog data types, and these are 4-state data types. You can see wire, reg, integer, time and real. And these are 4-state data types and real is a 2-state data type. These are the default values. Suppose if we declare any variable like wire A, that A will be having, it can have 4 different states like 0, 1, X and Z. And the default value of the wire data type will be Z. And you can also see here which are all signed and which are all take unsigned values. And compared to System Verilog, if we see System Verilog now, it will be having 2-state data types more compared to the 4-state data types. There is an introduction of logic, bit, byte, short int, long int, and short time and short real. These are the different data types available in System Verilog to declare any variable. And the default values of those also shown over here. Let us understand more about these data types. The very first one is logic type. You can see in Verilog, we don't have any logic data type. We have wire and reg. Always while declaring the output variables or to declare any intermediate signals, we will be having a confusion like whether we need to use wire or reg. To avoid that confusion, the one thing which Verilog that always leaves the new users like what is the difference between reg and wire. To avoid that, we can have a data type called logic in System Verilog. It will allow us to operate the variable as a reg and also as wire. When driving the port, which we need to use, and how about when we are connecting the blocks, is the confusion we have when we are using reg and wire. That can be avoided using logic data type. And this is a System Verilog data type. Improves the classic reg data type that can be driven continuous assignments, gates as well as modules in addition to being a variable. You can see here in the example, there is a module called logic data type, and we are giving an input as input logic rst underscore h. So reset is the input over here, and we have a parameter cycle is equal to 20. And here is the declaration of logic data type. You can see q underscore l, d, clock, reset underscore l. All these are logic types, and also our input is also a logic type. This is how we can make use of the registers inside the module and also the input port as a logic. And now we can assign clock is equal to 0 forever the clock is generated here. And also we can use this rst underscore l as a logic type to directly assign using continuous assignment. This is using clock which is declared as logic in a procedural assignment between initial begin end, and this is continuous assignment. You can see here assign RSTL is equal to not of RSTH, and this is a gate type, means the gate level, and this is instantiation. So all these indicates logic data type can be used even in the procedural assignment, continuous assignment. Q underscore L is driven by the gate, means when we are instantiating the gates primitives, and also while driven by the module. And then, as I said already, there are two state data types here in system Verilog. Bit B indicate this is a single bit variable, right? Similarly, if you want to extend any other value, we need to put the size over here. Bit 31 down to 0, B32 indicates B32 is a unsigned integer which will be having 32 bit in size. And int unsigned UI, int I, byte B8, short int, long int, integer, time and real. And the states with respect to 2 state or 4 state is given over here. And the maximum number of bits they can allocate is also given over here. Then comes, what is the difference between bit and byte? Byte by default it will take 8-bit signed integer values, and bit will take however the size we are going to specify here. Suppose if we specify 7:0 as a bit 7:0 some variable. Similarly byte something like B8, what is the difference? That we need to understand. You can see here bit 7:0 my bit vector, byte my byte value. Both are going to take 8-bit values only, but if we represent it as bit, it is unsigned. If we represent it as byte, it becomes signed value, right? And the ranges will be for the unsigned values, it is 0 to 0 or 1, 8-bit values. And if it is a signed value, it will take values from -128 to +127. And here is the example. You can see bit and byte, my bit vector, my byte value is given, and the same values we are allocating. 1010, 1010, it is a value, unsigned value of 170. And the same value if you allocate to a byte variable, you can see here my byte value is a byte, and this will be read as -86. Why? Because this MSB will be taken as a signed bit, and the value of this will be, if you represent it as a byte, it is -86. And if you add +10 to this value, it becomes -86 plus 10, so it is -76. To understand the positive and the negative number, go with this method. Positive number is 170, negative number is 86. How it is means, take this number, take 2's complement of this. How to take the 2's complement means, invert this as 0101, 0101 and then add 1. So this is the method. So you will get 86 now. So you have converted into 2's complement, means this is the -86 value, actual value. This is the negative value. This is how we can understand bit as well as byte data type. Then we have arrays in system Verilog. Array in the sense it is a collection of variables. There is a variable declared and such collection will be called as an array. And all the variables what we have in an array should be of same type, and we can access using same name plus one or more indices. Let us understand this more. There are different types of arrays in system Verilog. There are fixed size arrays, there are multidimensional arrays, there are packed arrays and unpacked arrays also. So in Verilog, it requires low and high array limits to mention the size of the array. It means int low underscore high 0:15. This is how in Verilog we are going to generally represent. But in system Verilog we can represent it with 16 directly. The both notations are same here, giving the same meaning. It means both are int data type with the name low underscore high and c underscore style. These are the two variables declared differently like this. So this also having 16 values starting from 0 to 15. This also having 0 to 15 values. And you can create a multi-dimensional fixed size array also by specifying the dimension like this. You can see here in this example, int type, array2 is the name of the array, 0:7 and then 0:3. Here we need to understand clearly that the first size what we are going to write is a number of rows. It is indicating rows. And the second value will be representing columns. You can see the matrix representation here, the array representation for multidimensional. 0 to 7 means there are 8 rows. So here you can see starting from 0 to 7, there are 8 rows. And 0 to 3 indicating there are 4 columns. And each and every element will be represented with 0. This is 0 cross 0, sorry. This is 0 cross 0. This is 0 cross 1, 0 cross 2, 0 cross 3. This is 3. And similarly, 1, 0, 1, 1, 1, 2, 1, 3. So as it goes, similarly the last row elements can be accessed using 7, 0, 7, 1, 7, 2, 7, 3. Here you can see the same type of declaration can be done like this directly using a compact declaration, that is 8 and 4. It indicates 8 rows and 4 columns. Starting with the first row will be start with 0, and similarly starting with first column will be start with 0. Suppose if you represent this verbose declaration in a reverse manner, 7 down to 0, the first one will be represented as 7, right? Now, according to the way we have represented here, if you want to allocate any value to the last cell, that is represented with 7, 3, we can allocate a value or set a value like this. Array 2 of 7, 3 is equal to 1. So this cell becomes with a value 1 now. This is how the multidimensional arrays can be written and allocate a value in System Verilog. Then we have unpacked arrays. These are also an unpacked values, unpacked arrays. Unpacked array in the sense the size will be represented after the name of the array. Remember, in this way, the size of the array will be represented after the variable name, then it will be called as unpacked array. Here also there are 3 elements here in the array. The size of each and every element will be 8 bits. But you can see here, unpacked array storage will be in such a way that it will be by default 32 bits, okay? But only the 8 bits is utilized over here because of the size mentioned as 7:0. So this is how the system will understand the unpacked arrays. Then we can understand how actually the array will be initialized with some values, okay? You can see here there are some examples here that will be called as array literals also. So int ascend 4, this is the declaration of the array. At the time of declaration only we can assign the values, or we can initialize this array. Ascend 4 means we will be having 4 elements. To initialize this array, we need to use this method. We need to use apostrophe, and then within the flower braces we need to provide the values. So the 0th element will be having 0, first element will be having 1, second element is 2, and third element is 3. This is how the 4 elements of the ascend array will be allocated with these values. Similarly, then we have int descend 5. We are not initialized any value over here at the time of declaration. Then we have one more array called int md 2, 3. It means there are 2 rows and 3 columns. That's why you can see here the 2 row values you can see here, and we need to indicate those rows separately. That's why there are 2 such values with apostrophe, and outside also we will be having 1 apostrophe. This is the way we need to allocate the values for multidimensional arrays. Then we have descend. We are assigning values for the descend array, which we have declared over here. Descend of 5 means it will take 5 values and it will be having 5 elements. So descend is equal to apostrophe 4, 3, 2, 1, 0 is the value we are allocating. Then descend 0 is to 2. It means only for the first 3 elements we will be assigning the values like 5, 6, 7. And also we can replicate the values using replication operator, like ascend 4 within the flower braces again 8. So 4 such values of 8 will be allocated to ascend. Ascend is having 4 elements, 0 to 3, that is 4 elements. So all the elements will be having the value of 8 now. 4 times we are writing 8. Then we need to understand how actually for loop and for each loop and $size will be used on arrays. These are array operations. How we are going to operate those arrays. Okay, we can use for loop. Here in the for loop, you can see here initial begin, bit 31 down to 0, SRC of 5, this is one array, comma DST of 5, this is another array. Source array and destination array with 5 elements, you can say. And by utilizing a for loop for int I is equal to 0, it means internally for a for loop, this I is an integer type. Okay, int I is equal to 0 and I less than $size of SRC, I plus plus, until or we can say I less than the size of $size of SRC means source array will be having 5 elements. So we are checking that whether I is less than that or not every iterations, right? So this $size will give us the information that how many elements are there in the this array SRC. So this function returns size of the array. So it is directly we are checking that I less than 5. And every iteration starting from I is equal to 0, we are doing SRC of I will be equal to I. I will be having a value 0 and that 0 will be allocated to the 0th location of the source array. And this continues until it reaches this condition. That is 5. All the 5 locations will be loaded with first 0 and then it will be incremented to 1. That first location will be loaded with 1 value. Second location will be loaded 2 values. Similarly, 0, 1, 2, 3, 4 values will be allocated to this source register. Then we have for each. For each within the braces destination of j we have written DST of j. Here the difference between for loop and for each loop you can observe here. While using the or a variable, internal variable within the for loop, we need to declare it as integer type, int I, and then we are assigning the value 0. But in the for each loop, here also we will be using one internal variable that is j. No need to declare this in for each. By utilizing any one variable, we can do the functionality in for each. No need to declare this as integer, as bit or whatever. So for each DST of j will be start with the initial value and let it be 0. So DST of 0 will be equal to source of 0 into 2. What we are doing means we are taking the 0th element of the source and multiply that by 2 and we are assigning that to the destination register. And this for each j will be started with 0 and it will go up to the end of the destination. It will be having 5. So it will allocate 5 values by multiplying each and every element of the source array to destination array. It means source of 0 multiplied by 2 will go to destination of 0. Again this loop continues until this destination of 5 ends. Start with 0, then j will increment to 1, source of 1 will be incremented with 2, multiply with 2 and it will allocate to destination. Similarly, this loop continues until it reaches all 5 elements. Then we have one more example here, how to initialize and step through multi-dimensional array. While using multi-dimensional array in a for each loop, we need to use the method like we need to have 2 variables. One is for row, another one is for column. That's why initial begin $display initial value we are displaying here, and for each MD is the one we declared previously as a multi-dimensional array. So that's why here MD is taken, and within the braces I comma j means it is a row as well as the column values variables, internal variables. Every time ij will be incremented because of for each. And here we are just displaying those values in terms of decimal, right? And then we are displaying a new value. Here we are allocating MD is equal to 987 for the first row, and for the second row 3 times value 5, right? Replicating the last 3 values. And there are 2 rows here. First row will be added with loaded with 9, 8 and 7. The second row will be replicating the value 5 3 times, right? There are 3 columns. And again for each MD I comma j, this is the right syntax we are again displaying. Here these 2 display statements are before loading this value we are displaying the content of MD, and after loading this value we are just displaying the content of MD, and we are utilizing for each loop for that, right? I and j will go till the end of the row values and the column values. And you can see here this is the output from the printing the statements. This is the first print. You can see over here the content, and this is the new values initially loaded with 0, 1, 2, 3, 4, 5. The new values are 9, 8, 7 and 3 5s. Correct. Then the next thing is, the next array operator is copy and compare. How we can compare the things and how we can copy the two arrays. Directly let us go to the example. Initial, begin. Again, source and destination arrays are represented here with 31 down to 0 size. And 0, 1, 2, 3, 4, 5, 4, 3, 2, 1 are the values currently we have initialized, source and destination. We can compare these two. Since these two are having the same size, we can compare these two as a condition in the if statement. If source is equal to destination, then it will display this message as it is, else it will display not equal, right? And also we can copy the content of the source into destination. It is like y is equal to a plus b. The right hand side a plus b will be calculated and then it will load to y, right? Similarly, dst will be equal to source means whatever the content of the source register, source array will be copied to destination. This will be called as copying, right? This is the copy method. And then change just one element of the array means we need to specify the indices perfectly. Source of 0 means 0th element will be loaded with the value 5. And all the values, if they are equal or not, we are checking here. You can see display the source percentage s dst, percentage s, it will fetch from here the string, it will fetch. It will compare source and destinations, and this is the conditional operator. If this is true, double equals will be printed over here, taken over here. Else, if this false, not of equals will be taken over here. This is a just display statement, and here we are just comparing the things. And our last four 1 to 4 are equal, means we are checking 1 to 4th element are same or not. Means the idea behind this is while comparing two arrays, the size should be same. Here we compared both contents, means complete contents, since those two are having 5 elements. Here we are comparing the part of the array 1 to 4 and 1 to 4, and this is how we need to compare. That is what we need to understand. We should not compare the different size with different size, right? You can refer this textbook, System Verilog for Verification by Chris Spear, and this is the reference textbook for this particular chapter. Thank you.